let's see if we can build a bit on some of our work with linear transformations. Let's say I have two linear transformations. Say I have the transformation S, that's a mapping or a function from the set x to the set y. And let's just say that x is a subset of, let me write it here, x is a subset of Rn. And let's say that y is a subset of Rm. Then we know if S is a linear transformation, it can be represented by a matrix vector product. So we can write S of x. Let me do it in the same color I was doing it before. We can write that S of some vector x is equal to some matrix A times x. And the matrix A, it's going to be x, whatever x we input into the function that we take the mapping of, it's going to be in this set right here, it's going to be a member of Rn. So this is going to be right here. X is, let me do it like this. X is going to be a member of Rn. So well, it's actually going to be a member of X, which is a subset of Rn, but I'm just trying to figure out what the dimensions of matrix A are going to be. So if this is going to have n components right here, matrix A has to have n columns. So matrix A is going to be, let's just say it's an m by n matrix. M by n. Fair enough. Now let's say we have another linear transformation. So actually, let me draw what I've done so far. So we have some set x right here. That is set x. It is a subset of Rn. Rn I could draw out there. And we have this mapping S, or this linear transformation, from x to y. So it goes to a new set y right here. Goes to a new set y. And y is a member of Rm. So the mapping x right here, the mapping x, you take some element here and you apply the transformation S, and I've told you it's a linear transformation, and you'll get to some value in set y, which is in Rm. And I said that the matrix representation of our linear transformation is going to be an m by n matrix, right? Because you're going to start with something that has n entries, or a vector that's a member of Rn, and you want to end up with a vector that's in Rm. Fair enough. Now let's say I have another linear transformation T. I have another linear transformation T, and it's a mapping from the set y to the set z. So let me draw. So I have another set here called set z, and I can map from elements of y, so I could map from here into elements of z using the linear transformation T. So similar to what I did before, we know that y is a member of Rm. We know that this is a subset, not a member, more of a subset of Rm. And these are just arbitrary letters. This could be 100 or 5 or whatever. I'm just trying to stay abstract. And let's say that z is a member. I'm running out of letters. Let's say z is a member of RL. Then what's the transformation T? What's its matrix representation going to be? And we know it's a linear transformation. I told you that. So we know it can be represented in this form. So we could say that T of x, where x is a member of Rm, is going to be equal to some matrix B times x. And what are the dimensions of matrix B going to be? X is going to be a member of Rm, so B is going to have m columns. And then it's a mapping into a set that's a member of RL. So it's going to map from members of Rm to members of RL. So it's going to be an L by M matrix right there. Now, when you see this, a very natural question might arise in your head. Can we construct some mapping that goes all the way from set x all the way to set t? And maybe we'll call that, let me call that the composition of, and maybe we can create that mapping using a combination of S and T. So let's just make up some word. Let's just call T with this little circle S. Let's just call this a mapping from x all the way to z. From x all the way to z. And we'll call this the composition. The composition of t with s. We're essentially just combining the two functions in order to try to create some mapping that takes us from set x all the way to set z. But we still haven't defined this. How can we actually construct this? Well, a natural thing might be to first apply transformation s. Let's say that this is our x we're dealing with right here. Maybe the first thing we want to do is apply s, and that'll give us an s of x. That'll give us this value right here that's in set y. And then, what if we were to take that value and apply the transformation t to it? So we would take this value and apply the transformation t to it to maybe get to this value. So this would be the linear transformation t applied to this value, this member of Ry, of the set y, which is in Rm. So we're just going to apply that transformation to this guy right here, which was the transformation s applied to x. This might look fancy, but all this is, remember, this is just a vector right here in the set y, which is a subset of Rm. This is a vector that's in x. So when you apply a mapping, you get another vector that's in y, and then you apply the linear transformation t to that, and then you get another vector that's in set z. So let's define the composition of t with s. So this is going to be a definition. Let's define the composition of t with s to be, first we apply s to some vector in x. So we apply s to some vector in x to get us here, and then we apply t to that vector to get us to set z. So we apply t to this thing right there. Now, the first question might be, is this even a linear transformation? Is the composition of two linear transformations even a linear transformation? Is it a linear transformation? Linear transformation. Well, there are two requirements to be a linear transformation, right? The linear transformation of the sum of two vectors should be the linear transformation of each of them summed together. So let's see. When I just say that verbally, it probably doesn't make a lot of sense. So let's just try to take the composition of t with s of, let's say, the sum of two vectors in x. So let's say I'm taking the vectors x and the vectors y. Well, by definition, what is this equal to? This is equal to applying the linear transformation t to the linear transformation s applied to our two vectors, x plus y. And what is this equal to? I told you at the beginning of the video that s is a linear transformation. So by definition of a linear transformation, one of our requirements, we know that s of x plus y is the same thing as s of x plus s of y, because s is a linear transformation. We know that that is true. We know that we can replace this thing right there with that thing right there. Well, we also know that t is a linear transformation, which means that the transformation applied to the sum of two vectors is equal to the transformation of each of the vectors summed up. So the transformation of s of x, or the transformation applied to the transformation of s applied to x. I know the terminology is getting confused. Plus t of s of y. We can do this because we know that t is a linear transformation. But what is this right here? This is equal to, all this statement right here is equal to the composition of t with s applied to x plus the composition of t with s applied to y. So, given that both t and s are linear transformations, we got our first requirement, that the composition applied to the sum of two vectors is equal to the composition applied to each of the vectors summed up. So that was our first requirement for a linear transformation. And then our second one is we need to apply this to a scalar multiple of a vector in x. So t of s, or let me say it this way, the composition of t with s applied to some scalar multiple of some vector x that's in our set x. This is a vector x, that's our set x. This should be a capital X. This is equal to what? Well, by our definition of our linear, of our composition, this is equal to the transformation t applied to the transformation s applied to c times our vector x. And what is this equal to? We know that this is a linear transformation. So given that this is a linear transformation, that S is a linear transformation, we know that this can be rewritten as t times c times S applied to x. This little replacing that I did with S applied to c times x is the same thing as c times the linear transformation applied to x. This just comes out of the fact that S is a linear transformation. We've done that multiple times. Well, now we have t applied to some scalar multiple of some vector. And so we can do the same thing. We know that t is a linear transformation. So we know that this is equal to, I'll do it down here, this is equal to c times t applied to S applied to some vector x that's in there. And what is this equal to? This is equal to the constant c times the composition t with S of our vector x right there. So we've met our second requirement for a linear transformation. So the composition, as we've defined it, is definitely a linear transformation. Now, that means that this thing right here can be written. This means that the composition of t with S can be written as some matrix. Let me write it this way. The composition of t with S applied to, or the transformation of the, which is the composition of t with S applied to some vector x, can be written as some matrix times our vector x. And what will be the dimensions of our matrix? We're going from a n dimension space, so this is going to have n columns, to a L dimension space. So this is going to have L rows. So this is going to be an L by n matrix. Now, I'll leave you there in this video because I realize I've been making too many 20-minute plus videos. In the next video, now that we know this is a linear transformation and that we know that we can represent it as a matrix vector product, we'll actually figure out how to represent this matrix, especially in relation to the two matrices that define our transformations, S and T.